to another OpenShift Commons briefing. As we are wont to do on Mondays, is create a space for some of the upstream projects to have AMA introduction sessions, and today the Kube-Scheduler is the topic of the day, and Wei is going from IBM is going to tell us a little bit about who he is and introduce himself, and then give us an introduction to the Kubernetes scheduler. So Wei, take it away, and we'll have live Q&A at the end.
Sure. Hi, everyone. I'm Wei Huang. I work for IBM, and I've been working in Kubernetes for a while. And the latest 2 years, I primarily work the upstream in the SIG-Scheduling. So right now I'm a co-chair, so I may know a little scheduling. So today I'm going to give you a Kubernetes scheduler introduction. Here's the agenda. So we will go through a very high level on what Kube-Scheduler is, what Kube-Scheduler does, and how it works. Oh, sorry, there's a typo here. How scheduler works here, and what's the latest development on the scheduling side. And the last part is because we are experiencing some component config API change in the later releases. So I want to highlight some configuration changes you want to be aware of in the last part. And the last part is how to contribute to Kubernetes scheduler. Okay, the first part is what scheduler is and what scheduler does. So basically, I can just use one sentence to explain what scheduler does. So what scheduler does is to do some magic to find the best node for incoming pod to be placed. So for example, in the upper images, so there is a pod which has the field node to now. That means it doesn't have a proper node to be placed yet. So then scheduler comes into the stage and do some magic and find the best node to put the pod. So you can see that the result of the scheduling is that you find the kind worker2 node for the pod to be placed. I have a demo a bit, so no worries. And here is the basic workflow, not only for scheduler, but for the whole Kubernetes components. So I will do a bit demo on this because I suppose you can see my screen, right? I have a con cluster with 3 workers. So right now there's no pod here. Oh, sorry. That's okay. Okay, no pod here. So I'm going to do something bad. I'm going to stop the Kube-Scheduler and the Kube Control Manager. So I have 2 clusters here. So I'm going to this control plane. And go because I'm using con, and inside it's a kubeadm cluster actually. So all the manifest is listed here. So I'm going to move the Kube-Scheduler out and also move the control manager out, so that it's expected to see the scheduler and the control manager gone. So there's only API server here. Okay, then let's try to deploy a deployment. Because why I use deployment? Because I want to show you how control manager works here. So I'm trying to deploy it. So what you can expect, the deploy API object will of course be created, but there's no pod backing the deployment. Why? Because back to our slides, once you create a deployment, it goes to API server, and API server, of course, do some basic check and position the API object. In this case, the API object here is a deployment, position it to the LSV, and then controller manager comes into stage and try to get the deployment object from the API server. But here, we intentionally shut down the controller manager, so there's no path creating here. You can see no path, and deployment manage the replica set, so no replica set either. Okay, so how to fix that? Let's move our controller manager back. And okay, there should be some time, a few seconds for the controller manager to go back. And once it gets back, it needs to do some internally, we call that caching sync up. So you may need some time to wait for it to get back. So while we are waiting, let's continue to the map. So the controller manager takes over and get the deployment event back, and internally it will create the object it needs to ensure the running part expect its desired replica numbers. For example, controller manager will try to see what's the replica set there and how many paths are managed by the replica set, and do some reconciling and make sure its state is desired. Okay, let's go back. Yeah, you can see that right now there is a, there's a replica set created, and also there is a part created, but it's pending. Why it's pending? It's because the scheduler has been shut down, so there's no component tries to do the work to place the part to the proper node. So let's explain how scheduler does. And now let's move the scheduler back. Okay. You can see the Kube-Scheduler is back and up for 5 seconds. Let me watch for the part. So it's expected that scheduler gets the incoming part and look at the status of whole cluster and find the best node for the part. You can see scheduler finds the current worker, the first worker for the part to be placed. And let's take a look at the API spec. So the most important field, as I mentioned, is the spec.node name. So once scheduler cites the node name to the current worker, then its job is now. And next is kubelet coming to stage, and every kubelet in each worker node watch some the path, and if the path spec.node name equals to its own node name, then it says, okay, it's me to take care of this part. So it tries to launch the underlying container runtime and launch up the containers. Then that is basically the part lifecycle. All right, so I just give a very high level on what Kube-Scheduler does and how it acts with us components, Kubernetes component, and how scheduler works inside. Let's take a look. So basically, there's two major phases the final decision is made. So the first is called filter. In the before, we call it the predicate, but I will use the two words interchangeably in this session. And if you look at some documents, if there's some a bit old document, maybe it's used the word predicate, but predicate and filter are the same. And right now, because we are doing some refactoring, we are more intended to use the filter and use filter plugin to describe this phase. So predicates hard constraints that you apply to your workload spec. For example, you may say, I want my pod to have a 2 GB memory and 1 core CPU. If there's no node fits, then just put my pod hanging there. I don't do anything else. So this is the hard constraint. It must be satisfied. And all the hard constraints are ended. If anyone is not satisfied, then the whole predicate will fail and your pod will be put back into the pending queue inside scheduler. And here is a link for the full predicate list. So I won't click here. You can check out later. And basically it works like this. There is an internal queue inside scheduler, and the queue pops the pod one by one. And once the pod comes into scheduler domain logic, and it will run all the registered predicates functions against each node. And of course, some node will fail and some node will pass. For example, here, there are 3 nodes will pass. So by the end of this phase, the output is that we get a 3-node list. We know that at least 3 nodes can fit the pod. Let me do some demo here. Let me use a very simple YAML, which add a node selector to the basic YAML template. So basically, the YAML tells me that I want to schedule this pod to a node which has a label kubernetes.io/hostname to kind worker. So this label will of course try to put the pod to the worker, right? Kind worker, the first worker. So let's take a look. Yeah, it works. So basically, this is how predicates work, which is the filtering works, because it's satisfied. So it's been put to the candidate worker. There's no other candidate. And if we change the spec a little bit to use, spec. If we apply a node affinity to the pod and say, so it gives some room to not only choose kind of worker, but here is just say, I don't want my pod to be put to the 3rd worker. So it can be worker 1 or worker 2. And there's also a hint here is that if you look at your spec, if there's some keyword like require, means it's a must. So it usually mapped to the predicates or filter phase of scheduling. That means it's a must. So let's take a look. So basically, the result is that, of course, it won't fit to the worker 3, but it maybe fit on worker 1 or worker 2. Let's take a look. Host 1 pod is put to worker 2. So you can see that maybe there's some magic happening inside the scheduler, try to balance the load allocation a bit, because we already have a pod landed in the worker, so it tries to land on worker 2, and maybe. So let's continue to look at the slides. So then after the filter case, as I mentioned, the output of the filter case is that we got a list of good candidates to be placed upon. But we want to do the step further to choose the best node for your pod to land on. So we call it this phase that as predicate. Sorry, we call it phase as priorities. Also, the latest term we use score, because it's just rank the candidates nodes from the previous stage. So all these constraints are solved. That means I prefer my pod to be, for example, I prefer my pod to be scheduled to a node which has SSD, or I prefer my pod to coexist or not coexist with some kinds of pod, etc., etc. So that we have some register priority. So each filter, each candidate node will get a score, and then we sum the score to find the highest score which the node has, and put the incoming part to the final winner. So as I mentioned, there may be some user-defined API spec that impact the priority. For example, I will show you a little bit. There is a prefer blah 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 spec in path spec usually means that this is kind of priority. And also there is some implicit default priorities. For example, if you create a path and the path belongs to for example, replica set, we will try to balance the paths belongs to the same replica set evenly. So that is some implicit settings. So you have to change that by, for example, disabling that kind of priority in the schedule configuration YAMLs. But if you don't have control for the config YAMLs, maybe you have to turn to your cluster admin to turn off some of the settings. So that is implicit default priorities. So the whole status, the logic works like this. The path has 3 nodes to be filtered, to be fit on, and then the priorities are on the candidates, and then the node 3 gets the highest score with 90, and then the path will be put to the node 3. So that is basically the second phase of scheduling. Let's go back to the demo. I have to show you a bit what it means. So there's another part I can put here. So again, it doesn't want to be put into worker 3. So it's required. So it's a predicate. And also I put the priority here. It's preferred during scheduling, ignored during execution. So because it's a scoring, so there usually comes with a weight. If not here, but usually specified in the Kubernetes configurations YAMLs. And that specify a soft requirement to be. So I prefer my path to be in worker 1 instead of worker 2. So let's take a look how it works. And yes, the soft constraint has been taken into effect. You can see that path2 goes to kind of worker. So after these 2 phases, so the whole life cycle of scheduler is done. Delete off that. And then maybe you are wondering, what if there's no candidate? That means if all the predicates fail. It's very possible, right? If your cluster is experiencing a high workload and almost all the existing workload has used up all the resources. So how can we resolve this? So in Kubernetes 1.10 or 1.9, we introduced the concept of priority class, or we call it priority or preemption. They are all the same thing. So let's take a look. So basically right now we have 3 nodes, right? Use. So next I'm going to deploy a deployment which has 1 replica and which has a low priority. If you don't specify the spec priority class name, it will be equipped with a default priority, which is 0. So in this default part with the lowest priority and request 3 CPUs. Right. Let me delete the pass. Okay, so this part is land on worker 3. So next, to continue the demo, I need to do some checks, which is the the other two parts, so that because I will show you a demo that the preempt part comes in, and I will just ensure that preempt only lands on the same node as the low priority, so that the preemption can happen. So let me tent now. I don't want it to be scheduled with any node part. All right, and then I will land into a preempter, which also requires 3 CPUs, because in total we only have 4 CPUs on one node. So and also this part has a higher priority. The priority class name should be matched for any existing priority classes. So by default, there's 2 system level priority class. The P1 priority class is created by me manually, and it has a value of 1. 1 is larger than 0, right? So let's take a look how it works. Because we have tented the other two nodes, so we will definitely has the only place which is the worker 3 to land on. So let's take a look. You can see right now it's interim state that is terminate, which you call the preempting the old part, which let me scroll up to show you the ID here. It's DPZPX. Right? The DPZPX is being terminated, and why is a new part is being created? Because container manager it's got notified that its old record is being deleted, so it's trying to spin up a new one. But no worries, this one doesn't have enough resources to run, so it will be pending there. And here you can see there's a interim status for the preempter, which is the nominating node of kind worker 3. It is because we don't do this preemption in one scheduling cycle. Once we found that we have a low priority path to preempt, we just set the spec nominating node to the preempter. Then we continue to the next scheduling cycle. So that is a bit different. But this state is very transient, so maybe you won't see that because it's very quick, this state. So you can see that the preempter, of course, preempts the older replicas, and then it lands on the worker 3. So this is basic how preemption works. I mentioned this power with priority class. Priority class should be created manually, and then the logic goes like this. The preemption happens on every node because there's no candidate node at all. And then maybe some nodes are good candidate for preemption, some existing paths, and some will come out to the preemption candidate. And also we have some internal algorithm to compare the preemption candidates to find the best node. For example, to preempt the lowest priority path as much as possible, instead preempt the higher priority path. All right, and let's go back to my demo. I want to untent the 2 nodes. Of course, because now we have 2 available nodes again, so it's expected that the low priority should have the proper node to be scheduled to. Yeah, there's no surprise. And let me delete the part. Okay, let's go to the next slide. So here's just a summary on the key features of scheduler. Like if your workload spec asks some specific resources, no matter it's the default resources like CPU, memory, storage, or some extended resources like nvidia.com/GPU or whatever extended resources you define, the resource fit request is going to the scheduler. And also, if your pod has some toleration, and toleration, the matchup with the 10s also down in the scheduler, as well as the node selector, node affinity, pod anti-affinity, and in 1.18, we have introduced the pod topology spread. I will mention a little bit later. And also preemption is a built-in feature, not specific to any kind of workload, but applied to every pod. If you want to have preemption, you can define the priority class. And also some storage related feature are also related here. For example, if you have a storage class which is of the type wait for the first consumer, so that if you create a PVC, then the PV won't be created when the first consumer comes into. So that phase is also happens in the scheduler because it wants to delay the PV to PVC binding to the scheduling phase. So that is basically the key features of scheduler. And what's new? The first new features we introduced is the pod topology spread. So pod topology spread is trying to resolve some limitation of the existing features like pod affinity and pod infinity. So pod affinity is like, I want my path to be scheduled to a topology domain as much as possible. So basically, you can't control how many I want to be placed into the same topology domain and how much I don't want. And pod anti-affinity is another extreme case. That means you can only schedule one pod to a defined topology domain. For example, if you define if you define the pod anti-affinity into two zones, then each zone can only have one pod. So in between these two extreme cases, there's a lot of room that you want to manage the balance or imbalance degree of how your workloads behaves, so that we introduce the pod topology spread. Give you a quick demo here. So the pod topology spread add a new API spec called the topology spread constraints, and has some API fields here. The when unsatisfiable, there's two values right now supported. The first one is do not schedule. It's a hard requirement. That means if it doesn't satisfy this requirement, which means if the balance degree is larger than 1, Max Skill described the imbalance degree, then I don't want to schedule. And of course, you can make it a priority, which means a softer requirement, which you can use the keyword scheduler anyway. So you can basically use the two. You can as much as constraint as you want. So right now, I just demo there's one constraint. So basically here, I want 3 replicas. I want them to not that imbalanced. So most strict balance mode, which only one topology can larger than the other by 1. Pass evenly across these 3 nodes. And yes, it works like this. But if I want to scale it to 9, on the 3 nodes evenly, right? Let's see if it's the case. It's pending. Why? It's pending. Usually we use Kubernetes kubectl describe part to see what's the error message Kube-Scheduler says. Oh, it says 3 nodes didn't match part topology spread constraint. And there are actually 4 nodes here. Why there are 4 nodes here? Because the master node we also count as a node. So the fourth part will definitely try to place onto the master node. But master node, as you know, master node has some special tend to avoid the incoming part to be placed, right? That makes sense because in the kubeadm's deployment, the master node deploy like this. So that we need to change the spec a bit so that we want to explicitly exclude the master node. So I just use this trick and node affinity to exclude the master node. Let me just apply this. And it has 3 requests. Let me scale it again. Yeah, give it a seconds. Okay, you can see it. Now it works perfectly. There's 9 paths and worker 1, there's 3 paths, worker 2, 3 paths, worker 3, 3 paths. Okay, here's the basic how the part topology spread works. And there's a blog explain this feature in details, and there's some advanced usage on this feature. So if you're interested, just check it out. Another feature we came up recently is called multi-profile scheduler. I will demo this a bit later. So basically the motivation is because of the limitation of multi-scheduler. So we use the support multi-scheduler. Multi-scheduler means in addition to the default scheduler, you can have as many scheduler processes running outside or whatever, running somewhere. And so they works together by identifying which kinds of path each scheduler will cover. For example, there is a path spec called spec.scheduling name. So if you don't specify that, the default scheduler will take over. But if you explicitly specify that spec, the corresponding scheduler will take over those kind of paths. So you can easily think that there will be some racing issues. For example, if there's only 1 CPU left in this node, and the 2 schedulers are both trying to schedule its own path to that path, competing for that remaining 1 CPU, and then of course we'll kind of have a timing racing issue, and that is very difficult to be avoided because these 2 scheduler processes are running independently. They are not running in memory to sharing something. They're totally different binaries. And also, right now, the suggestion we give to user if you run in multi-scheduler is that this racing case can be mitigated by dividing your cluster into several pods, and each pod is governed by each scheduler. So this can mitigate the issue, but not resolve the issue totally. For example, some advanced scheduling features like pod affinity, pod topology spread, this feature doesn't just use a single node to do decisions. It has to look at the whole cluster, look at the interpod and the internode connections to do the right decisions. So in that case, this feature can also cause the racing issues. So how can we do that? How can we resolve this limitation? The proposal we came out is using a
Hey, Wei, I'm not sure if it's me or if it's you.
Scheduler.
You're
Oh,
dropping
sorry.
out. Your voice is dropping out just a little
Oh,
bit.
sorry.
You could repeat that last phrase.
Okay. So the solution we propose is using a multi-profile mechanism, so that we still recommend you use the scheduling binary and just one scheduling binary, and within that we give you some API spec to define the profiles you want. So each profile is like a scheduling flavor. For example, this flavor wants to be the part to be more impact, that flavor to want to be whatever takes more priority on some other features, whatever, so that the binary is compiled there and the profiles are defined there. They are just working into one binary, so there's no racing issue. And also the consumers can specify their workloads to using what kind of schedule profile they want to use. So that works like the same. So basically we want to resolve this issue like this. But this multi-profile scheduler cannot be done without a major code refactoring inside scheduler. So in the last 3 or 4 releases, the most important thing is code refactoring, and we refine each phase of the scheduling. So in the before, we just have 2 phases. One is filter, one is score, and now we have a more fine-grained phases like pre-filter, filter, pre-score, score, normalized score, etc., and preemption. And also we sort of separate the binding phase apart from the main scheduling cycle. So the binding cycle works as async routine, sort of. So that is why the profile can only happens when we raise up the scheduling framework. So framework is just we redefine some internal logic and expose the extension point that the consumer can consume and write their own logic. And then those kind of logic can be put on top of our scheduler to combine, so compile to a new custom scheduling binary, which has some the capacity that you want, not the default capacity. But 100% of the default schedule capacity is kept. So this is a scheduling framework. That is the major 3 things that we are developing recently. So the next topic is config Kube-Scheduler. I think this must be this demo. How much time I have left? 20 minutes. I will try to use 10 minutes to do the demos. Okay, I have 2 clusters. Let me change to another one. So this account with extra amount. Yes, I have 3 nodes and don't have. Right now, I'm going to another cluster's control plane. Kubernetes manifest. So let's take a look how the scheduler is launched up. And take a look at the default scheduler configuration files. It's because kubeadm is special. It's because it's using a static part, but that doesn't matter. And the main parameters here is here. So it's still using the command line argument style. But recently, not only in scheduler, but also in kubeadm, Kube Manager, we just use YAML to describe this command line arguments. We use like scheduler use a scheduler component config, which is YAML. You can pass in using the -- config, and most of the command line arguments are also defined there. So right now, the 2 arguments coexist, but maybe in the future we will totally remove the command line arguments, but keep the scheduler component config. So let's move this out. And I have a new configuration file. So this is the same configuration files. I keep the most of them, but just using the -- config to pass into the scheduler, and also use the extra mount so that the manifest I use here can be mounted directly. So I'm going to, oh, and also I need to mention a bit on this YAML. This YAML is using the V1 Alpha 2 component config. You can see the con here, scheduler, Kube-Scheduler configurations. So basically, it just defined some common command line arguments here, like the Kube config, the leader election, and additionally, we define the profiles here. So you can see here, I keep the default scheduler, and also I can give some other flavors like image first. Image first is to give a very high weight on the image locality. Image locality is a priority function that say, okay, if this node has the image, for example, it has a you want to have the nginx image, and once the next nginx path come, I prefer to use this part because it can save the image polling time. So this is easy to understand. And also I defined another flavor called binpack. So by default, the node resource list allocated priority is defined, which means I try to spread the overhead on each node. So put the path as even as possible. But it's not the case for like cluster autoscaler, because this kind of scenario wants to use the resources as much as possible. And if not possible, they will spin up a new node. So in this case, they want the path to be more binpack. So I use the opposite of priority called node resource most allocated and give it a higher score. And of course, in some extreme particular case, you just want to maybe don't want any score plugin to participant, because you may think the filter is already good enough, so you just want your part to randomly land on any candidates. That may be possible, we don't know, but I just use a demo here. Okay, so you can, so that I'm going to move, what's that, mount. Okay, I'm going to mount that here. Yeah, scheduler. Oops, it's error. Not quite sure why. Oh, it still has a configuration file here, so let me move this out. Scheduler. Maybe I made some mistake there. Take a look at the.
It's because it's live, Wei.
All right. So I just want to show you that once you define the new style configuration file, then you can run workload like this. So for example, a bin pack. So I'm going to demo that. I just want to deploy 10 paths, and the 10 paths will land on the same node. So here is that you should use the scheduler name to one of the profile names you define. And of course, the Ubuntu here is that you launch one image and then you launch a second. Maybe the second one will be placed on the same node there because we use the profile flavor image first here. So it will try to use the node which has already the image loaded on there. So I'm sorry that maybe I made some mistake on the configurations. Anyway, so we can give a try. So one thing I want to mention a bit here is that if you're still using the lower version of Kubernetes, the multi-profile is not supported. It's only supported on 1.18. If you still use the old version, maybe you have still to use the V1 Alpha 1 version, and in that case, a deprecated field called algorithm source.policy is used. So that policy YAML you cannot define, of course, you cannot define multiple profiles, and also the predicates, you have to use the keyword predicates and the priority to define or modify some in-tree default settings. So this thing you must be aware of. And the Wilma Alpha 2 is just what I tried to demo. And yeah, multi-profile just work like this. So the spec.scheduler no name right now adapted to two kind of mechanisms. You can use the multiple scheduler just like what you used before, and also you can use the multi-profile in one scheduler. But in the Kubernetes long-term roadmap, we recommend that you use just one scheduler binary to avoid any racing issue and define the profile inside the scheduler. All right, here's the last section, how to contribute to the SIG scheduling. So some high-level definition of this SIG is defined here in charter.md, and we have several projects. The priority is the default scheduler, which is shipped with the Kubernetes release. And also we have some sub project like this scheduler. This scheduler is initiated by Red Hat, so it's trying to resolve the problem that along with the running of your cluster, some balanced situation may be broken. For example, at this moment, at the point of scheduling, maybe your workloads are evenly balanced, but maybe some nodes have been shut down unexpectedly, so that path got moved to other nodes. And maybe sometimes those nodes get recovered back. But at this point, scheduler doesn't do the rescheduling for you. And we don't have a priority on supporting that in default scheduler. So you have to use some external component like this scheduler if you really care about the balancing or some specific strategy you want to comply with. So use this scheduler. And the second one, scheduling plugin, is we want a marketplace for you to hold the customized plugin for extending the existing scheduler compatibility. So the scheduling plugin is also a subrepo, which is to follow the scheduling framework to build custom plugins to fit more innovative requirements, scenarios, etc.
So Wei, are there any pardon my naivety, are there any custom scheduler plugins already
Yes.
available? Okay.
Yes. For example, Alibaba contributed a co-scheduling plugin, which it tried to scheduling group apart together. This is a typical requirement from the batch workloads in AI and machine learning field. And also, they raised another proposal to consider elastic resource quota. So, because right now resource quota is defined in the admission hook. So admission hook means if a part specify, I want to use this CPU, I want to use this memory, but it fails, it still keep the request. No other incoming parts can come. So it's also a common requirement to kind of delay the evaluation of the part request of the quarter to the scheduling phase. So yeah, some common requirements and the plugins are developed there.
Waleed in the chat is mentioning that Portworx also comes with its own scheduler called Stork. So there are a few other examples of other schedules there. Yeah, I hadn't heard that. And a lot of the content that you've covered, I didn't really have a good background in. So thank you very much so far for today. This has been really good.
Yeah. And yeah, I think this is almost for today's session. And the last 2 slides are just some links you can check out offline. And yeah, that's it.
There was a question about the pros, if you would educate us on the pros and cons of kind versus Minikube.
So I prefer kind. I think kind maybe it's a superset of Minikube. So basically, Minikube just launch up a one node cluster, and inside there is a virtual machine. If I understand it correctly, so there's one machines, and you can operate with that virtual machine that has one node there. So of course, it has some cons that if you want to do some scheduling development, or just want to try some scenario that must have multiple nodes, you cannot do that. For example, if you remember that if you want to debug the priority, if you only have one node, of course the priority won't happen because there's only one choice. There's no need to do the scoring, the ranking sort of things. And I do like kind because it can be useful in the open source development, in the in-tree development. So once you change some source code, you can build your current code base into a kind node image and launch up that. And also some other features are supported in kind. Yeah.
So I think I'm looking at the Q&A here. Waleed's adding some commentary on the Minikube here in the side. Minikube can use Docker containers as nodes now, and kind challenges ingress. So I think you've mostly answered the question about Minikube versus kind.
Mm-hmm.
And I'm not seeing one other. There's another one just came in that what will be the impact if we use 2 schedulers?
Yeah, that is this page mentioned. If you use 2 scheduler, the racing issue cannot be avoided, even if you manually separate the cluster into 2 parts and each scheduler just govern that part. Yeah, the 2 reasons I just mentioned here, because if you don't divide the cluster, it's possible that you try to schedule, the 2 scheduler try to schedule the same part at the same moment to compete for that resource, because there's no distributed log on deciding which scheduler can win. Right? So the final arbitrator is just the kubelet. Kubelet just is a single points, right? The kubelet will finally decide which one, maybe the later one will fail. So that's the case.
So if I have a hybrid cloud deployment, so I've got some of it running on bare metal, some of it running on hosted someplace, am I necessarily having multiple schedulers?
I'm not quite sure on that field, but someone has explored that field using scheduling framework to manage the resources on a multiple cluster. I have a tweet on that.
There's a
Where's my
tweet for everything.
Yeah,
This is just to prove it.
someone just pinged me that they use the scheduling framework to manage the multiple cluster on the scheduling tasks.
Ah,
So yeah,
so you're
this
using,
one.
yeah, cool.
Yeah, this one.
Yeah,
Yeah.
Admiralty, like he released it I think last year.
Yeah, so
Is that
Ravi,
Ravi? Yeah,
Yes, I just I'm sorry.
so excuse me, again, my there, Admiralty IO is that a custom one that they've done, or is that an open source one? Where is that coming?
I think it's open source one.
Okay,
It,
good.
it is open source, yes.
Yeah.
Yeah.
Cool. Cool. Ask and ye shall receive.
There is also Univa, which is an HPC resource scheduler company. They have worked with Red Hat in releasing an open source universal resource broker last year.
That's right.
I'm not sure what.
Yeah. I'm not sure the grid engine people. Yes, I know them. But yeah.
They are in Canada.
Yeah. Just Canada rocks. Canada days. Every day. I'm like, we're all getting excited.
So basically they spawned this company, NavOps, and they are doing like data science, cloud migrations, but in their heart, they are an HPC company, and they have open source, what they call universal resource broker, which basically fits in the scheduler area.
Ah. Oh. Now I'm making the connections between all of these projects, and that's what this is all about, is really trying to figure out how all the pieces in that wonderful CNCF landscape fit together. So if you could put your last slide up again, the one that had how to get a hold of you, that would be great. And I know the scheduler SIG is meeting on a regular cadence. So if folks are interested in this or interested in just reaching everybody, the Slack channel is probably the quickest way. If you don't want to wait for a SIG meeting to get a hold of people who are keen to talk about this topic. And when is your next SIG meeting?
It should be just this Thursday.
Okay.
10 a.m. PST.
Cool. So that's where you can get more information about this. If you're working on a scheduler plugin, whatever it is that you're doing in the space, please come. I know more bodies on SIG meetings is always a good thing, and that's helpful. And we'll get some more.
If you have some items to discuss, you just put the item here in the next meeting agenda. We'll go through that.
Perfect. Well, thank you. I know that this is one of those ones that I'm going to have to watch again so I can get through it again. But the documentation is pretty good around the scheduler stuff, so please do take a look at all of that. And I'm just going to make a note that we will be off the air tomorrow at noon. If you're looking for a commons thing, there is a talk on ACM. That's going to go long, so we're going to take the day off, and we'll be back on the 1st of July, and Karina Angel is going to host a talk on IBM DB2 Warehouse MPP on OpenShift container storage with Red Hatter Michael St. Jean, who's going to bring some special guests along with him too. So that'll happen on at this same time slot on the 1st of July, which I'm happy that I have a co-host because I can take the day off and celebrate Canada Day. So That will be my holiday. And then we will be off the air again on Friday as it's the US holiday. So lots of great stuff coming up. You can find all of it on the events calendar on at commons.openshift.org on the events calendar. So take care, everybody. And Wei, I will try and get this video. If you send me your slides, oh, well, you already did.
Sure.
I have your slides. I will get this.
I have
video.
I have an updated one, as well
Okay.
as all the YAMLs uploaded
Okay.
to the GitHub.
So send that to me, and I'll try and get it to you for by Thursday for your SIG meeting, so that people can wander through it there too. So thanks again, everybody, for joining us. I don't see any more questions coming in, so really appreciate it. I'm going to try and have every one of the Kube-Sig chairs on Mondays over the coming months. On the 13th, we have the Fedora CoreOS team coming. Then my Open Data Hub is coming, and I just keep going to do upstream projects on Monday. So if you have other things that you want to talk about, or anybody from one of your sub projects, Wei, throw them my way, and we'll put them on and give them some airtime. So thanks again, everybody, and thanks, Chris, for producing. This is really good.
Thank you.
And Nimesh, next time I'm going to get you to talk too.